piecewise functions, evaluation and graphing. Before we get into the evaluation and graphing process, we should discuss what a piecewise function is. So at this point, we've seen functions that have a single function rule, say f of x equals 2x squared plus 5. There's only one rule, and this whole function is defined by this expression, 2x squared plus 5. So the geometry of the curve in the xy plane is dictated only by this. Now, what you're going to see in a piecewise function, maybe you guess, is that we're going to have multiple pieces to the graph, hence the name. So the notation you're going to start seeing is we'll still have this function notation at the beginning. So it doesn't have to be f, it could be g, h, just like any other function. But then after that equal sign, you're going to see this brace open up. And instead of just having a single function rule, we're going to have two or more. So we're going to have, say, rule 1, rule 2, and there's no limit to how many rules you have, so we'll just go up to, say, rule n. And then next to each rule, we're going to have these inequalities. So we'll say inequality 1. And that inequality is going to tell you the x values that are associated with that specific rule. So three main things to look at. What is the function name? What are the rules that go to that function? And then for what x values does each rule apply? So to give you a more concrete example, we might see something like this. F of x equals 3x plus 4, x squared minus 1, and say 5. So in this case, our piecewise is going to have 3 function rules. And then next to it, we might see that this first rule, 3x plus 4, is only going to be applied when the x values are, say, less than negative 3. And the second rule will be applied when the x values are between negative 3, or I'll say greater than or equal to negative 3, and say less than 5. And then the last rule will be applied when x is greater than or equal to 5. So that's just one example. But again, to interpret what this is saying, we have a function f of x. Our input variable is x. And you'll notice that the variables in all of the rules, if a variable is present in one of the rules, does match the function notation input variable. So you see the x's are used here. Now our last rule doesn't have a variable. That's a constant function because there is no variation in the curve. So it's just going to be a horizontal flat line. So for this first 3x plus 4, again, that's only going to be applied when we're looking at x values that are less than negative 3. The second one is only going to be applied when we're looking at x values that satisfy this inequality. And then the last one only applies when we're looking at x values that satisfy that last inequality. Now, there's also no limit to what type of functions are present in your piecewise. So the 3 functions I chose for this, and we'll be seeing primarily at this point in the year, this first function is a linear function, the second one's a quadratic, and the last one's a constant. But as we progress through the course, we're going to see more complex functions inside. So just to give you a heads up, we could see stuff like an exponential in there, so maybe 2 to the x minus 4, or 5, sorry, and then maybe cube root of x plus 2. And then whatever the inequalities are after that. Okay, but now we have an exponential function. Now we have a cube root function. So there's no limit to what type of function we put inside. So now that we know what the piecewise functions are going to look like, let's look at how we evaluate them. So I have 2 examples here. We have f of x and g of x. So we're going to look at f first. And we're going to say, what is the value of f at negative 2? And what is the value of f at 5? So we see this f of x as the function name. We know that what's inside that parentheses are our input. So when we see notation like this, our function evaluation notation is telling you to substitute negative 2 in for x. So to evaluate the first one, f of negative 2. We have 3 function rules for f of x. We have negative 5, 4, and 12. So all 3 of these rules are constant functions. You'll notice that none of them have variables in them. And all that means is that the function itself does not vary, right? So nothing's changing. It's staying at the same output value for all x's in these inequalities. So the thing to keep in mind with function evaluation of piecewise is the fact that they are functions. And therefore, for every input, we know by definition our function should have only one output. So the common mistake at the beginning when students first evaluate piecewise functions, if they're unfamiliar with what this actual notation is representing and they forget about the definition of a function, is they want to evaluate at every single rule in the function. But we have to remember that the rules are only followed for specific x values. So to evaluate the piecewise, we have to determine of the inequalities that we see in the piecewise, where does that value that I'm evaluating at fall under? So -2 of these three inequalities, x is less than or equal to 0, between 0 and 3, or greater than 3. Which one does that satisfy? And I think you would agree that -2 falls in this first inequality. And therefore, we're going to look at this first function rule for the evaluation, and only that rule. Now, there's no x to substitute in for, but again, if we understand what a constant function is, no matter what the input, the output is all the same, hence the name constant. It does not vary. So our answer is -5. And we can see that from that single output of -2, we only got one answer, -5. So let's look at the second one, f of 5. So I ask myself, of the three inequalities, f of 5 falls under which one? So we can agree that 5 is greater than 3, so it will fall under this inequality. And therefore, it's going to follow this function rule. And again, there's no variable there. So that tells me that the outputs are the same for all x values in that region of the graph, or that fall under that inequality. So f of 5 equals 12. The output should be 12. So again, single input, single output, so this still satisfies a function. So I shouldn't see multiple outputs per input if we're calling this a piecewise function. So now let's jump down to g. We'll do this example because variables are involved. And let's evaluate g at the same two values. So let's say we want to do g of -2 and g of 5. G of -2. We're going to determine what function rule should be followed if I'm evaluating at -2. So what inequality does it satisfy? -2 is less than 5. So I'm going to evaluate this first function rule at -2. There is a variable here, so you're not going to write 3x plus 4. I want the actual output value. So what you have to do is substitute -2 in for x to that single rule. So we're going to take 3 times -2 plus 4. When we simplify following order of operations, we're going to get -6 plus 4, which is -2. So when I plug in -2, the output is -2. So there's your answer. G of 5, what inequality does it satisfy? Is it less than 5, or is it greater than or equal to 5? It follows this, and therefore we're going to follow this function rule for g of 5. Again, don't give me the rule, give me the actual output value. So I'm going to substitute 5 in for x, and we're going to get 5 squared minus 3, which is 25 minus 3, and that gets us 22. So always keep in mind that we're working with functions. So every time you plug something in, you are expecting a single output, assuming that input value is in the domain. And how do you determine what rule to follow? You have to determine what inequality that input value satisfies. That's the rule you're working with. So that's how you do piecewise evaluation. Now let's jump over to graphing. So this first graph is going to be similar to what you're going to see right now. I will do a second example with different types of functions that we haven't seen at this point in the year, but you will see in the future. So after this one, if you feel comfortable with how the method used to graph, you can jump to the end of the video to see the process written out, and you can take notes on that. So here's our piecewise. We want to graph this thing. So the first thing we're going to do is recognize we have 3 function rules. So I'm going to have 3 parts to my graph. Now, we want to pay attention to when we are going to graph these specific rules, or where we're going to graph these specific rules. So when x is less than 2, I'm graphing the first one. When it's between 2 and 4, I'm graphing the second one. And between 4 and 8, I'm graphing the third one. So a very helpful first step when graphing piecewise functions is to break up the coordinate plane into sections so you know where you're graphing each rule. So to show that, you're going to input vertical dotted lines through the x values that you see in the inequality. So every number in the inequality, you're going to put a vertical dotted line through. So the first one I see is positive 2. So I'm going to draw a vertical dotted line through 2. And then I'm going to draw one through 4, because that's the next number I see. And also through 8. So all we did to start is just break up this graph into sections. And what's helpful next, again, optional step, you can just write above each section what rule should be applied in that section. So anything less than 2, so to the left of positive 2, we are going to graph 2x squared minus 2. So in that section of the coordinate plane, I should see that graph. In the second section, between 2 and 4, I should be graphing 4. And in the last section, I'm going to graph negative 1/4 x plus 5. Now you'll notice that there's going to be nothing to the right of 8 because there is no rule defined for when x is greater than 8. So there's going to be nothing in that part of the graph. And that can happen. There could be gaps between. So that's why it's really important to pay attention to the values in the inequalities and set up those dividing lines to begin with. Now, once we have this part established, so we broke up our coordinate plane into sections, we then need to determine where these graphs hit these dotted lines or where they intersect these dotted lines. They are not going to cross over these dotted lines. So we input these dotted lines to set boundaries. Because if you just graph all 3 of these functions as individual graphs all at once that cover the whole coordinate plane, you're going to see that this function would fail the vertical line test with your end product. And we have to keep in mind we're graphing a function and therefore it should pass at the end. So we got to determine where these parts hit the dotted lines. The way we do that is we're going to take the values in the inequalities that are associated with the function rule, and we're going to plug them in. So I want to know when this first expression hits the value of 2, that vertical dotted line at 2. So all I do is I take 2 and I plug it in. So down below, I'm going to say 2, I plug it in. When I simplify this, 2 squared is 4 times 2 is 8 minus 2 is 6. So what this tells me, the input was 2 and the output was 6. That tells me I have a coordinate of 2, 6. Remember, we can interpret coordinates not only as locations in the graph, but also an input-output for a function, because we can format the coordinate as x f of x instead of x y, and we can use that as input-output, but also the location where we're going to have our intersection. Now, that's the only dotted line that 2x squared minus 2 is going to intersect. It's not going to intersect the one at 4 or 8 because it shouldn't cross over that first one. Now, what about where does 4 hit 2 and 4? Well, looking at these two numbers, we have to look at both of them. So it's going to intersect 2 dotted lines because it's contained between those 2 boundary lines. There's nothing to plug in. But again, going back to the evaluation, we know that it's always going to be at an output value of 4 in that region. So for input 2, I know the output is going to be 4. For input 4, I know the output is going to be 4 because it's a constant function. And then lastly, we're going to have to do some evaluation for these last 2 points to figure out where that linear function negative 1/4 x plus 5 hits those 2 dotted lines. So we'll do some evaluation below. So we're going to have negative 1/4. I'm going to plug in 4 first. And then below, we'll plug in 8. 4 times negative 1/4 is negative 1 plus 5 is 4. So input 4, output 4 gives me a coordinate of 4, 4. Then input 8 is going to be a fourth of 8 is 2. Negative 2 plus 5 is positive 3. So we're going to get input 8, output 3. So I have all my points of intersection. Now, before you go to plot them, what we then have to do is determine whether or not these coordinates or these points of intersection are going to be included or excluded in our function. And the way we determine that is based on the inequality signs themselves. So if we have less than or greater than symbols associated with that input value for that specific rule, that's going to indicate that the intersection point is an open circle. It's not included with that portion of the graph. But if we have less than or equal to, or sorry, greater than or equal to or less than or equal to, we're going to have closed circles because that point of intersection will be included with that portion of the graph. So when we evaluate it at 2, 6, or we found the intersection of point 26 for this first inequality, or this first boundary line in this first expression, we see that we just have a less than symbol. So that would indicate that this first coordinate is going to be an open circle. 4. This one in the second expression, the second rule, we see a greater than symbol. So this is also going to be open. This one, a less than symbol that produced this coordinate 4, 4, that's going to be open. The second point, 4, 4 down here, we see greater than or equal to for this function rule. So that means this point 4, 4 is included in this part of the graph, but not in this part of the graph. So now we're going to close it up. Then lastly, at the intersection point with the vertical dotted line at 8, we see a less than or equal to sign, and therefore that intersection point is included as a part of that region of the graph. So we're going to close that in. Now that we've determined those points are open or closed, we can now plot them. So at 2, 6, I'm going to plot an open circle. Then at 2, 4, I'm going to plot an open circle. Then at 4, 4, I'm going to plot an open circle. And then it says at 4, 4, plot a close. So the next question is, well, what if it's open and closed? So we're at the same coordinate for these points of intersection for these two parts of the graph. The close is going to fill in the open. Okay, so closed overrules open. And then 8, 3 is our last point, and that is also closed. So we divided up the graph to start. Then we determined points of intersections with our boundaries. Now we just have to figure out what these function rules look like in each region of the graph. So when we have function expressions, part of our piecewise, that include constants and linear, those are the easiest ones to graph. So let's take a note that constant functions, we should already be aware, are just going to be horizontal lines through that y value of 4. So we're just going to see a horizontal line. So there's really no math to do to graph that. So that middle region, where it's supposed to follow this function rule, the output is always 4. So I'm just going to see a horizontal line there. So all I have to do is just connect those 2 points. And a constant function is linear, so it should be a straight line. It just has a slope of 0. Then for the last one, the negative 1/4 x plus 5, that is a linear function. It's in that slope-intercept form where you have a slope of negative 1/4 and a y-intercept of 5. Now, the y-intercept isn't going to exist here. It's never going to cross the y-axis again because it gets cut off by that boundary. It doesn't pass over. But the good news is with linear functions, all you need are 2 points to graph the function and just draw a line that connects them. Well, the good news is here in this specific example, we already have the 2 points where this lines hit both boundaries. So all I have to do is draw a line that connects them. And to verify that this line is correct, we can see that it does have a slope of negative 1/4 if we just want to count our rise over run. We're going down 1, right 4. Now, the last one that's a little trickier, or requires some work, it's not that tricky, is that we need to figure out what this quadratic looks like. Now, this quadratic has curvature. So quadratics look like these U's, they're like these parabola shapes. Okay, so it's going to look like one or the other. Now, when we work more with quadratics, you'll know that this one's going to open up. So we're going to see a U like this. But how do we get the points to show that curvature? What you're going to do is select x values that are in that region of the graph. So say we select 1, say we select 0, negative 1, negative 2, to get an idea of what the output should be at those x values. So we have to plug in these chosen x values into our expression. Whatever comes out is the output or the y value of our coordinate. We plot those points and we should see some curvature. And we want to get enough points to show a full depiction for the graph. So don't just do 1, do multiple if we know there's curvature in the graph. So I'm going to plug in 1 first. So if we do 2, 1 squared minus 2. So I'm just plugging in 1 to this first expression because that's the one we're trying to graph right now. So 1 squared is 1 times 2, so we're going to get 0 here. So input 1, output 0. So there's a point. So I'm going to go plot a point at 1, 0. I'm going to plug in 0. 0 squared is 0, times 2 is 0, minus 2 is negative 2. So we're going to have a point 0, negative 2. I'm going to plug in -1 next. So again, this isn't enough because I should be aware that the quadratic is going to be a U shape. So it feels like I'm getting just part of it right now. -1 squared is +1 times 2 is 2 minus 2 is 0. So when I plug in -1, I get 0. So now that I'm back to 0, it looks like the U has made its turn. So let's get at least one more point here. So I'm going to plug in -2. So -2 squared is +4 times 2 is 8 minus 2 is 6. So we're going to get -2, 6 as a point. And the good news about parabolas is they're symmetric about some axis of symmetry. So we can see that there's symmetry going on here. So we had a point of 2, +6. Now we have 2, -6. We had 1, 0, -1, 0. So the vertex point of our parabola, or the lower high point of our U shape, we did end up graphing at input value of 0. And we're going to see something like this. Okay, and that quadratic is going to go on forever because I could continue to plug in negative values and have no issues with the output. So there is a depiction of the piecewise. A final thing that you should do to check. I've graphed each region, shown curvature with enough points for the quadratic. For the constant and the linear, all I need is 2 points to connect those. Just keep in mind constant is going to be a flat horizontal line. The last thing that you want to be aware of is we are graphing a function. So again, this thing should pass vertical line test, and it does. This does not fail vertical line test. If yours does when you initially graph, something went wrong. So you're going to have to double check where you crossed over boundaries. Did you put the boundaries in the right place? Were you misevaluating expressions at the wrong input values, things like that. So it should pass vertical line test at the end. So that's what our piecewise looks like. 3 pieces to the graph, 3 expressions, 3 rules, and we can see 3 distinct parts. So now I'm going to jump over to another example. Again, you can skip over this example if you feel comfortable with this. This example that I just did is going to be very similar to what you're going to see in this unit. So make sure you know how to graph quadratics, constants, and linears. Then later in the year, we'll see more complex functions like I'm going to do in this example. But again, if you feel comfortable and you want to jump to the end to write down notes, feel free to do so. So in this example, we only have 2 rules. So I'm going to work a little quicker now that we have this process established. The first thing I want to do is break up my coordinate plane into sections. So I'm going to put a vertical dotted line at all the numeric values in the inequalities. The only number I see in the inequalities is 2. So I'm going to graph a vertical dotted line through 2. If it helps you, I'm now going to label each region to make sure I'm graphing the right rule in the right section. So when x is greater than 2, that means to the right of 2, I get to graph the square root of x minus 2. When it's less than or equal to 2, so to the left of it, I get to graph 2 to the x. So this first function is a square root function. The second one's an exponential. Now, once I've labeled my regions and broke up the graph, I now have to determine where do these functions hit that boundary line. So I need to substitute this value in to the expression it is associated with. So I'm going to substitute in 2 to the square root of x minus 2. We're going to get the square root of 0, and the square root of 0 is 0. So input was 2, output was 0. So there's my point. Then determine if it's open or closed. Well, the inequality sign that it's associated with that expression indicates that 2 is not included in the domain of that expression or that part of the graph. So therefore, I'm going to have an open circle for this first point, and I can plot that right now. So at 2, 0, I'm going to have an open circle. Then I'm going to substitute 2 into 2 to the x. So it's going to be 2 to the second, which is 4. So input of 2, output of 4. Now 2 is an included domain value for 2 to the x. I can plug it in, I get a valid output. So it is included in that region, so we're going to put a closed circle there. So at 2, 4, let's put a closed circle. Now, both of these functions have curvature, so they're not linear or constant. Therefore, I'm going to have to find some additional points in each region to model that curvature. So you're going to select x values in each region and evaluate the function at them to get the corresponding y value. We'll plot the points. Usually it's good to do at least 3 points if you know curvature is present. The more, the better. With the square root function, because I have to actually take a square root, my objective should be that when I plug in x values, I get perfect squares underneath there. That's going to make my life easiest. So if I plug in, say, 4, I'm going to get square root of 2, but I don't know exactly where the square root of 2 is. But say I plug in 6, when I do 6 minus 2, I'm going to get the square root of 4, and I do know how to take that. So hopefully you get that idea. When I plug in 6, I get 2. So I'm trying to set up perfect squares under the square root so I can easily evaluate it and get an idea of where I should plot it. So 6, 2 is a point on this curve in this region. Now the next perfect square that I would set up would be, say, 9. And that would require me to plug in 11. And 11 is off the board, right? So that's really the only point I can do. If you want to put in 11, you're going to get square root of 9, which is 3. So if we had 10 and then 11 and 3, it's going to be somewhere over here. And when we get more familiar with radical functions, square root functions, you're going to see curvature something like that. So that part's completed. Now we're going to do 2 to the x. So when we get used to exponentials, we'll notice some properties, but this is a good review of exponent rules as well. So I'm going to evaluate at 1 to start. So I got to pick x values that are to the left of 2, because this expression is defined when x is less than or equal to 2. So let's plug in 1 to start. So 2 to the first equals 2. So when I plug in 1, I get 2. So let's plot a point. Now let's plot the output at 0. So if I plug in 0, anything to the 0 power is 1. So 0, 1 is a point. Now when we start plugging in negatives, this is a good review of exponent properties. So if I plug in -1, well, negative exponents can be made positive as long as I take the reciprocal of this base value. So if I flip it, I can make it positive. And 1/2 to the power of 1 is 1/2. So input of -1 got me an output of 1/2. 2 to the -2. That's the same thing as reciprocal raised to the positive version. And what is 1/2 squared? That's 1/4. So when I input -2, I got positive 1/4. We'll do one more. 2 to the -3. That's the same thing as the reciprocal raised to the positive version of that exponent. So 1/2 cubed, 1/2 times 1/2 times 1/2 is 1/8. So when I input -3, I got 1/8. And if you were to continue this process for all these negative numbers, you're always going to notice that the output is greater than 0. Because if I take a positive value and raise it to any number exponent, whether it's 0, a positive number, or a negative, the output is always positive. So this graph is going to stay above 0. And in fact, it's never going to reach 0. It's never going to get to 0. So we're going to graph this thing, and it's going to get really close to the x-axis and never quite get there. And the terminology for that we'll discuss when we go to the exponentials unit. But for now, you could play that out for multiple x values if you wanted, but this is what the graph should look like at the end. Now, as a final note to piecewise graphs, make sure that your graph passes the vertical line test and it does not cross over these boundary lines that you set to start, and mine does not, and it passes the vertical line test. So this is what the graph would look like. So to conclude the video, I'm going to give you the graphing procedure if you want to take notes on this. So the first thing you should do with graphing is we want to divide up the coordinate plane into sections using the vertical dotted line. So we're setting up boundaries. The locations of the vertical dotted lines come from the numeric values in the inequalities. So we know we have that section in our piecewise notation that gives us these inequalities. Every single number you see in the inequality, you should be putting a vertical dotted line at. And it's okay to have regions of the graph where nothing is going to be present in that region. So we could have blank or regions of the graph, okay? Like we saw in the first example, there was nothing beyond +8. Once we've set up our boundaries, we want to determine where each piece or rule intersects the dotted lines. How do we do that? We take the value at that dotted line, so the numbers in the inequalities, and you plug them in to the piece that that inequality is associated with. If there are multiple numbers in the inequality, you have to plug in both numbers into that piece to figure out where it hits the boundary on the left and on the right. And remember, because we're working on a coordinate plane, the number you plug in is the x value of the coordinate. The number that comes out as a result is the y value of your coordinate. Once you've figured out your intersection coordinates or your intersection points, then determine if those values are open or closed. And that's going to be dictated by the inequality sign. So less than or greater than is open circle. Less than or equal to or greater than or equal to, you're going to have closed circle. Next, find additional points in each section to accurately model the rule for that region. So pick x values in each section, evaluate the expression for that section further to determine additional points to get an idea of what the curvature looks like. Again, good news is if you have constant functions or linear functions, you shouldn't need many more points. In fact, if it's constant, you should just be able to draw the horizontal line at whatever y value is present for that constant function. And if you have linear, well, if the linear is contained between two boundaries, you should already have your 2 points to graph it. It should be the intersection points. But if it only has one boundary line for the inequality, it goes on to the left or right forever, well, then you're going to need to only find one more additional point. You only need 2 points to draw a distinct line. So you should already have one of them from the intersection. All you have to do is find one additional one. Now, if you have a function with curvature, like the quadratics, you're going to want to make sure you find at least enough points, 3, 4, 5, to model the curve. So again, I say found by evaluating the rule at the x values in that section or in that region of the graph. And then the last thing you want to do is verify your graph does represent a function by checking to see if it passes the vertical line test. Okay, so make sure it passes the vertical line test at the end. So there's a video on how to evaluate and graph piecewise functions.